Hi, I'm Jeongjang from PostTech, and today I present our research, ArithMotion. Imagine you're joining a VR session with two of your friends. Your friends are using the high-end VR devices with full-body tracking. But you only have a mobile VR devices like a Google Cardboard. In that case, while your friend moves naturally, you are unable to move your avatar. This creates what we call a nonverbal expression gap. To deal with this, many platforms provide emotes, which is the predefined set of motion like clapping or waving. But they can't reflect the ongoing context, which makes communication less expressive, less alive. So from here, our key question is this. How can you create socially aligned and open-ended user motion from the user's simple input? To address this challenge, we introduce our key concept, peer-relativity, inspired by our everyday interaction. And let's watch the video to see what it is. Imagine that your friend raises his fist for a friendly fist bump. Naturally, you follow and bump fist back. So in this case, you express your delight by mimicking your peer's motion. Now in an alley, a thug blocks your way and threatens you, saying, "Get out of my turf." In this case, instead of mimicking his motion, you take a defensive stance, reacting in the opposite way. So in this case, you express your fear by expressing the complementarity of your peer's motion. In daily interaction, we constantly express ourselves either by mimicry or complementarity of the peer's motion. This is what we call peer-relative motion, the motion that is expressed relative to the peer's motion. Peer-relative motion enables expression that reflect the context of social interaction, something that traditional emotes cannot achieve. For example, when your friend raises his fist for a greeting, emotes may only let you wave your hands. And when someone threatens you, emotes might only offer a crying gesture. But peer-relative motion enables more open-ended and socially aligned responses that fit the ongoing interaction. However, to let VR users express such peer-relative motions, we need an intuitive and simple medium, one that naturally reflects this concept. To achieve this, we use arithmetic as a metaphor, which is a simple yet powerful way to formalize how one motion can relate to another. For instance, if your friend's motion is represented as M, your corresponding motion, the fist bump, can also be M. This is like the identity in arithmetic. If a thug threatens you, your defensive response can be represented as -M. This is like the negation in arithmetic. And if you are very happy to see your friends, you might exaggerate the peer's motion as a 1.5 M. And if you feel shy, perhaps only a small response, 0.5 M. And both cases are expressed as the scaling in arithmetic. So in this way, a user's motion can be expressed as a simple arithmetic operation based on the peer's motion in social VR. And now let me introduce our system, ArithMotion, which brings pure relativity into real interactive settings with simple interaction. It consists of models that can actually generate pure relative motion and an arithmetic-inspired mobile system. And I first introduced the models that realize pure relativity. The first component is the motion latent space, which enables continuous control or blending of motion. We build the latent space by training the variation autoencoder. And for example, if you want to scale up the Pierce motion, we calculate the corresponding embedding vector and decode it to the final motion. So as you can see here, it results in a more exaggerated motion. However, the motion latent space only captures the geometric aspect of motions like continuous control or blending. When we try to produce the negative motion, simply reversing or scaling the geometry is not enough. But negation requires the understanding the meaning of the motions. So that's why we developed the negative motion generator, which produces the negation of the given motion. So first, the input motion is converted into the text, and this text is transformed into the sentence with the opposite meaning. And finally, this opposite text is converted back into the motion, resulting in the negated version of the original motion. So these models enables generating pure relative motion with the user's arithmetic input. And we developed the application for mobile VR users to express peer-relative motion, and let's see how users interact with it. In VR, users can see a peer who is coming to the user while stretching their arm. And to express peer-relative motion, the user touches anywhere on the screen, then UI appears. You can see peers' avatars are shown in the UI. Then slide up the scale of the peers' motion, so in this case, this peers' motion would be the input motion. And when you release your hand off the screen, then you can see the resulting exaggerated motion is rendered on your avatar. And we implemented more UIs to support various arithmetic operations, but for more details, please refer to our paper. And we conducted the user study, and we asked participants to use both emotes and the ArithMotion system to examine how users use both systems complementarily. They participated in the home party, like meeting in front of the house, touring the room, watching the basketball game, and then having a birthday party. And in the beginning, participants tended to use emotes more often because they are simple, familiar, and suitable for casual interaction, such as greeting others in front of the house. But as the session went on, they gradually used ArithMotion more frequently as interaction becomes more open-ended and context-specific, like eating together in the party. And both systems were used in a balanced way, complementing each other's strengths and weaknesses. And this creates a synergistic effect. We evaluate the user's pattern, usability, and observability of generated motions. But for more details, please refer to our paper. To wrap up, there are many motion expression methods in commercials, but I want to note that ArithMotion is not intended to replace or compete with existing works. But our system is designed to complement them and coexist with each other, providing a new option for expressing open-ended motion to users, even with minimal interaction capability. So this is the end of my presentation. Thank you for watching.